we're going to go to this address. This time it's the right one. And we will exercise our, so Armstrong, who was a sort of famed weightlifter in the 60s and 70s, said he started out his journey towards being a weightlifter by, they asked him, like, how did you get such big muscles? And he said, I flexed my 60-pound weakling muscles, and eventually they became big muscles. You could tell I even flexed my 60-pound weakling muscles. But we're gonna go through the exercises of downloading a model again and loading it into anyone. So try this one. It's tinyurl.com. And no materials this time. Out black spot. Okay, so there we go. ABM Bootcamp 20. Oh, I should turn on the screen share. I stand remiss. And here we go. Okay, and if the electrons cooperate, we should be here at the right place, and so it is. Okay, so now I'd like to get example models. And now I'd like you to go down to, you'll have to scroll down. If these are alphabetical like they are for me, if they're not, you can sort them with this little thingy. And there should be one called SAR agent-based for PLE. Do you see that? Okay. If you double click on that, you should be put in here. And I'd like you to, again, go download this. Again, you can right click on it and click download. So again, how did I do that? I went to that address there, and I went to, here we go, boom. And I went to example models. Those who downloaded it, you can start to fire up any logic and load it in there. But I just want to make sure no one's left behind. I clicked on example models, SAR agent-based for PLE. I just scrolled to find that, and then I right-clicked and downloaded. Again, if you have trouble downloading, you can double-click and then see it in all its glory or gory, and then you can do download, okay? There we go. Okay, who needs help? Who needs help? Who needs lunch? But no, okay, who needs help? Okay. People need help? Don't be shy about raising your hand for help. A phalanx of TAs will assemble to help you if anyone needs help. We are well situated with TAs in might and number. Okay, so we downloaded it, and now let's go to AnyLogic. So where's my AnyLogic? Here it is. There it is. Okay. I'm going to close this one. I don't really need this one around right now, so I'm going to close it. You can go up and close it, or you can do file, close others, for example. I'm going to do open, file, open, and I'm going to load this in. And here we go. So it's going to load in, and it's going to show us the structure of this model over here on the left-hand side again. And you notice that this model, like the one we saw earlier, has a set of constituent parts. To wit, it has a depiction of a person and one of Maine. And I'm actually not happy with this model as it is right now. So well, okay, I want to do this in a better way. Okay, fine. So we'll okay, come on. Okay, now I screwed this thing all up. Okay, don't you worry about it. I was going to delete this thing. We'll do that in the reverse order. This unfortunately has kind of the trick shown in it. Okay, so you should see this. If we go to person, you should see this person can be in. What do these things depict? Can anyone say what is this? What do these things depict? They're possible what? States a person could be in. And what are these lines between the states? They indicate transitions. Yeah, they indicate a person who is susceptible. If there's a person who's susceptible, they can become infected, they can become infectious through an infection transition. And we'll learn soon enough how to make all this, choreograph all of this. And this is someone, if they are infectious, they can recover. Okay, and this, as we've learned, means a certain chance per day. In this case, it's a rate of 1 divided by average illness duration. Chance, I can't stand that. Okay, they will recover with a chance of that per day. They have a certain hazard rate. And then after a certain amount of time recovering, they'll have a certain chance per day of 1 divided by 150 days of going back to susceptible. So what this means, it turns out, is on 150 days on average, they will become susceptible again, having recovered. So they'll wane, their immunity will wane. Okay. Now, this is just a depiction at a person level, but remember that these models are much more than, atomistic depictions of individuals. They place those individuals in context. And you recall that I uttered from this very floor that these models put a premium on agent-agent and agent-environment interactions. So if we go to main, we double-click on main and we go down main, we'll notice that we have an environment in which these agents are situated. And if you scroll up here, scroll to the left, you'll see there's a population of people. And if you were to click on people and you were to go look, I'm going to introduce this properties window now over here to the right. If you don't see that, you can sort of click on this and it should show. If you still don't see it, you can do view properties and it will show up. It says there's an initial number of agents is given by the total population, and then they're put into place. Okay, and you'll notice we're going to count the number of susceptible, infected, recovered. So what I'm going to do is I'm going to run this. I'm going to run this model. Remember, models are not merely depictions in an explicit, shareable, critiquable fashion, refinable fashion. They are enactable depictions. They are precise enough to be run. That's what makes them a simulation model. So I'm going to right-click on simulation. I'm going to run. I'm going to say, what is the logical consequence of this theory of the world? What's this logical consequence of this theory of what's going on out there? And I'm going to press this button here. It's going to say run, and it's going to take a little bit of time. Oh, there's a message in the chat. Oh, Danica needs help. Could someone help? Yeah. Awesome. Okay. So what we've just depicted is some rather fulsome behavior. This is on full speed mode. So I'm going to turn off full speed mode here. I should have. I'm sorry, folks. I'm just thinking the best way to do this going forward. Let's press. So down here, there's a better set of controls. These will control how the model runs. On the second one to the left is a square button, and some of you will recognize that if you press it, it will stop the model. Okay, and I'm going to ask you to stop it in a way that I want to set it to a lower speed. So when it started, it was on this highest virtual speed. This was sort of grayed out. That means it was running as fast as it could. I don't want that. I want to catch up with, I want to let my brain catch up with the computer. I don't want it to go as fast as it can because it will outrun my brain. I unclicked this side here, or it's a gap. So I unclicked it, okay? Great. And now I'm going to run it. Having unclicked that, I'm going to run this model by pressing that go button there, okay? And what you're going to see is a situation where there's a field of agents initially who are initially susceptible, And I'm clicking on this and pulling it down so I can see it. And you'll notice that infection is spreading. Agents here, to sort of make this clear, you don't have to follow this, but susceptible is yellow, red is infectious, gray is recovered. So can anyone say what's going on here? If yellow is susceptible, red is, by the way, I'm pausing it for a second here. Red is infectious and gray is recovered. What's going on? Can anyone give a sort of a intuitive description for what's happening here? What do we see?
Spreading.
Yeah, it's spreading. It's spread from a small number at first, and it's spreading outward. Now, you'll notice that this sort of crenulated surface here, this sort of quasi-circle, that's emerged. That's a pronounced feature of this. Whence did that come? Where is that in the model? Can anyone say? Where is that in the model? I'm asking a trick question. That's an emergent feature, right? Like there's no place in the model that says build a circle of a certain size and have it grow or something like that. That actually comes as an emergent feature of this. When I say this, what I mean is the fact that people start susceptible, they can become infectious. When they're in the infectious state, they can send at a certain rate of contact, they can send others who are their random neighbors in space. Think northwest, southeast, etc. The cardinal and other directions, 8 directions, send to their neighbors. It's probably worth checking. It's this in a 4 neighborhood or 8 neighborhood. Wade, maybe you can check if you get a chance. But it's an 8 neighborhood. Okay, so ladies and gentlemen, so here we have people start susceptible. If they become infectious, they can spread it to others. They'll send messages to others, see the send infection message that they're sending. If one of those others to which they send the message is susceptible, they too will become infectious. See that? And after a while, an infectious person will recover. And after a while, they'll go back to susceptible. So ladies and gentlemen, this pattern that we see there is emergent. That's not pre-programmed into the model. It's not in that first transition down from susceptible. It's not in the recovery transition. It's not in the contact transition. It's not in this state or that state. It's kind of a emergent factor which emerges from all of them, and it's occurring spatially. And if we plotted out the number of people who are susceptible or recovered over time, if we were to go and plot that out here, as we could do above, and I'm going to scroll down, you'll see that it's also arcing out a behavior over time. By the way, I'm clicking this to allow it to speed up a bit. Now I sped it up to about 10 times higher. And you'll notice that we have a rise in the number of infectious, a rise in the number of recovered as well. And the number of susceptible are way up there. So here we're having a spread of infection over time. Now, this model is playing out the logical consequences of what's going on. What can anyone say? What's going on in the interior now? What's happening here in the interior? We see something different. What's going on now? They're becoming reinfected. And what's allowing them to get reinfected? Yeah, okay, so they're susceptible, but it takes 2 to tango. What else does it take for a susceptible to get infected? Yeah, contact with some residual infective, right? So there's kind of these successive waves of infection which are occurring because there are some residual infectives still around from the earlier wave that stuck around that are leading to these kind of patterns of successive infection within the population, right? If the infection were to die out sooner, for example, from an individual, they'd infect fewer people, but there might also be fewer of them left around. And you can see that the patterns each etched out by this model over time in terms of the number of susceptible or recovered or infectious. It's rather complex. It has some regularities, but it has some chance variations over as well, right? And it looks like, roughly speaking, it's going to a little bit of an equilibrium. Now, we could run this model, though, with some different assumptions, right? One assumption is we could have a fast recovery. If you go click on the fast recovery side, and I'm going to click on that and change this properties to expand parameters here. You'll notice that for the simulation, if I were to look at its parameters, its average illness duration was 10. For fast recovery, the average illness duration is 2. What do people think will happen now? Anyone? How would that change things? Sorry? How would that change? If before we had an average illness duration of 10, and now we have an average illness duration of 2, what would that change? Okay, they recover faster, that's true. Yeah, that's kind of based on the average illness duration, but how would that lead to changes in the emergent behavior, do you think? Anyone want to posit a guess? Okay, waves may become more frequent, so that's a good thought. Okay. Anyone else? I hear lower contact. Okay, so yeah, there'll be maybe fewer people infected by each infective before they recover. Yeah. Other things. Now, you could see how hard it is to think, like, what exactly is going to happen here, right? How is it going to change what we see spatially? How is it going to change what we see in terms of those graphs? Of course, this is what a computer is really good at. It's turning these concrete assumptions into, computers are great at doing really dumb things quickly. That's the truth of the matter. And so let's run this. They just excel at this. So let's run it. Oh, I need to stop. I should have stopped it from going as fast as possible. Sorry. Oh no. Let me stop it, and I want to turn off that virtual speed mode. That was bad of me to put it on. Okay. Okay. So we're running it here, and we're going to go down and look at where it started. It actually starts down here in the lower right. Come on. Oh no. Okay. Get up there. There it is. Okay. So the suspense builds. We can actually speed it up with this. Here we go. Okay. So here it's speeding up. Notice any difference from before? Yeah, fewer reinfection. Okay. And what do you see here? Oh my gosh. See a bunch of susceptibles, a bunch of recovereds, but who don't you see? Infectious ones. Oh my gosh. Infection is basically recovered. Everyone recovered and they're all susceptible again, and the infection has died out, right? Okay. Now, how about slow recovery? Suppose it took 50 time units for them to recover. How do you think that would change it? Anyone? Sea of red. That sounds like a good thought, but no one can stay red forever. So what's going to happen after that? They're going to turn. Hey, come on. Okay. So on my phone. Yes. Okay. There's the sea of red. Okay. Not to be confused with the Red Sea. Okay. Okay. It's spreading outwards here. What's going on in the interior there? What's going on there? Isn't that interesting? What's going on there? Well, what happened to these waves? Yeah, why aren't the waves existent? Can we tell a story? What's happening? Yeah. There's not enough susceptibles to make a wave, right? They never get a critical mass to sort of become susceptible enough to cause a big outbreak. So it actually goes to sort of an equilibrium, a bad equilibrium. Number of susceptibles is quite low. Number of infectives is quite high, but it goes to kind of an equilibrium much, much faster. Now, you could play with this. You could create, by the way, you could very easily do this if you were to right click on fast recovery and click copy. How did I do that? I right clicked on fast recovery. I did copy. You could also, click on it and do edit copy. That's equally good. Now I'm going to right click on this whole model and say paste. Just like that. And now I have this copy of it, and it's called fast recovery. And I'm going to call it medium fast recovery. You can see I'm not very good at naming things. And I'm going to make them recover in time. Let's say, what was the original one? Anyone remember? What was the original? 10, was it? So I'll make it 5. There we go. There we go. Okay. So the original was 10. You could see that here. And now medium fast will be 5. What do you think will happen now? Well, we could run it, right? We could say run. Okay, so you're adding these scenarios where we're changing this assumption about recovery. And I could play this out, and now we'll see something that's, yet another variant. So now we have people who are recovering somewhat faster, and the question is, will it die out? Remember when recovery was really fast, it died out. Remember that? There was no one left over to infect anyone after that. Notice there are some people in the interior here still who are infected, and they might infect others there. But the question is, will it catch, right? And so we can kind of play it out. So I am viewing the chat. Yes, indeed. So what do you think? Is it gonna die out, or is it gonna catch? What do you think? Die out. It died. It completely died out. If you ran that many, many times, would it always die out, do you think? The first round? Maybe sometimes it would stick over just by chance, but probably eventually it will die down after 1 or 2 times, etc. So you start to see the effects of stochastics here, right? I'm going to show, so I will also just note that you could look at an extreme case where you look at an incredibly slow recovery. I'm going to look at an extreme case where waning of immunity is just not going. What would happen if people didn't wane immunity? What do you think would happen then? Suppose we modified the random seed. Yeah, the random seed is a random. So the random seed gives rise to a random number generator. So if you go to any of these, and if you were to go to randomness, you could see you can use a random seed, a fixed seed, or a custom random number generator. Basically, when we generate randomness with computers, we're actually making use of what's known as pseudo-random number generators. And there are very sophisticated ways for generating, and there are very simple ones. This uses a standardized mechanism, and it uses standard what are called Java libraries for this. This random seed here will essentially keep each run distinct for all intents and purposes. It'll be just chance. I think it depends on things like the exact timing with which it is invoked and something about the time of day, et cetera. But essentially, this is each one will run uniquely. Will run uniquely. A fixed seed would run it again and again with the same random number sequences generated. And you could use a custom generator, which is a more advanced method. But essentially, these are, the fixed seed will allow you to repeat an experiment exactly, including in its stochastics. So it's completely reproducible, whereas a random seed would allow you to sample different realizations of the same experiment. So I had asked a question though. Yeah, I had asked a question. Suppose we were to delete waning of immunity. What do you think would happen? Anyone? That's a structural change. What do you think would happen? Here we've been changing parameters. Suppose we were to delete that altogether. Gone. And why will it die out much faster? What's the story? Good. Anyone who's gotten recovered, there's no way for them to become susceptible again. So they can't be reinfected. So they will stay as this block of recovereds. They will be a firewall to a spread of any infection, and they won't be spreading it to any others. And as a result, they're going to prevent any spread. Even if they were next to some susceptibles, they'd kind of block them from getting exposed through them. So if we were to delete that and we were to run the normal simulation, what you would find is, you're exactly right. And your name again? Gabrielle. Gabrielle's precisely right. So models help us think through, these combination of factors. They help us check our intuitions. They help us cross-check our kind of best guesses for what's going on. And they help us quantitatively study over what spheres of, say, parameter values certain dynamics are observed, like it dies out, and under what ones, others are observed, like it goes cyclically, or it just goes to an equilibrium very quickly. I just ran it without that waning of immunity, and notice, what's that thing in the middle? One susceptible, one very lucky susceptible, sitting there protected by all their buddies right around them, and they survived the pandemic. Yeah.
State chart to have someone immune prior to the infection, like near the susceptible state, could there be a probability that someone is also immune prior to that? They're just natural.
Oh yeah. So great question, and we'll talk about some similar things this afternoon a little bit, but generally, so the question was, for those online, there was a question, is there a way in a state chart like this to represent the fact that there might be some people, for example, before any infection, they might be already sort of have a pre-existing immunity to infection or pre-existing resistance to infection. So there might be some group that are not susceptible to infection. The answer is absolutely yes. And we could capture that in a couple of ways. When we build up state charts this afternoon, one thing that we'll talk about, which I'm glossing over here, is often one of the things you're going to want to think about is where people start in the state chart. And this actually started everyone here. And actually, this transition is to allow the model to sort of say, hey, you're the unlucky starting. This one is, one has to start infectious. So it basically sends a person infectious to the infectious state. You could send some people initially to the recovered state and just say, hey, you start recovered. But often what we would do is, I'm not asking you to do this, but often what we could do is we could go to our palette, and we'll go here to the agent palette, and we'll have a branch transition here. And we could have, for example, a certain number start start recovered, and some other number who start susceptible. And we could divide people up. And in fact, we could have some people start infectious. And we could have another recovered state, not called recovered. We could have it called, pre-existing immunity or whatever, and just have a certain fraction of people start there. This little diamond shape is indicating a sort of conditional situation where you can roll the dice. Which way do they go? So a certain fraction goes one way, a certain fraction goes another. It doesn't have to be rolling the dice, but that's a very common use. You could have some rule that sort of routes different people to different states here based on chance or based on characteristics or other circumstances. So yes, you could have other states in which people could initially be present. Hope that's helpful. Yeah. Okay. I should note for those shopping around for other platforms, again, not here to sell any logic. I will say that state charts are starting to get fuller billing and other agent-based modeling packages. For example, in Repass, they've also emerged as a favorable way to draw out logic associated with agents, and for good reason, because they're very helpful for diagramming the simple sort of simple but powerful and very general mechanism of having agents evolve according to rules among a set of states and depicting it visually. Okay. So those are all the comments we have for this morning. This afternoon, we're going to be building up some models just like this. We're putting together models of this sort of complexity this afternoon and working towards more sophisticated ones yet. Okay. So that's for today. But before that, we have your lunch. So I'm asking for a TA to go over. So all the TAs have meal cards as well. And I need a TA to go over with the participants and to take care of the admissions. So TAs, who's good to volunteer? Come on, don't you want a free lunch? Okay, I'm going to draft a TA if there's, okay, Larissa, thank you. Okay, so here we have a set of meal vouchers. And you can bring them over for the others, and you can just give them to the cashier in the front. For all the others, one per person. Okay, awesome. I will be watching the room. Santa's got to work in Santa's workshop, but we'll be coming back. I think we'll ask if people could come back in about an hour. That will be great. 1:30, and we'll reconvene and get going on a bunch of hands-on stuff. Okay. So thank you, and we'll see you back here about 1:30. And for the